All right, so 6, 3, 4, and 5 are going to be like completely new things to you. Like law of sines and cosines, you maybe got your feet wet with it last year, but 6, 3, and 4 are vectors, and then 6, 5 is something completely different, imaginary numbers. So the good news is you're all on the same level playing field. But if it looks completely foreign to you, that's normal, okay? So 6, 3 is called vectors. We're going to kind of lay the foundation as to what that is and how to find component form, magnitude, that kind of stuff, and then some application. So a vector is, it almost looks like, well, it is a segment because it has endpoints, but it has direction. So it has like this little arrow. Notice the arrow is not at the end. This is not a ray. A ray would have it at the end and a ray would never end, okay? A segment has 2 endpoints, which is what this has, but that arrow has direction, and by direction, it's almost like slope. So like it's a change in y and a change in x on a coordinate plane, and then it also has length, which is called magnitude. So what's important is that one, there's 2 ways to identify or to write a vector. The first is using the endpoint, so the 2 letters that form the endpoint. Sorry, let me change my colors. Like in this example, the PQ and the little arrow over it, the arrow part or the half arrow part goes over the Q. That name tells you, just like similar to array, that name tells you that it's going to start, the initial point is P, and then it moves towards Q. Yep.
Can we write it with like the full arrow, or does it have to be?
It doesn't, I'm not going to get on you for your format of how you write it. Just know that when you read it, it will look like that.
Okay.
Yeah. The other way, and more common, to be honest with you, is using a single lowercase bolded or italicized letter. So this ray is either called vector PQ, or it's called vector V.
Why is it V?
So it's like they use V, they use U, they use W. That would just be you would see it named either on the shape or it would be named in the top like that. So you can call it either thing, okay? Usually, and you obviously don't have to bold it when you're writing it out or italicize it. Just know that that's how you'll read it. The first thing we're going to find is the component form. And the component form is the change in x followed by the change in y. So it's almost like the slope with the denominator written first and the numerator written second. It's separated by a comma, and it's in these little brackets, which are supposed to be pointed, okay? They are not parentheses. They are not the squiggly braces. They are different. So we do the second, or the terminals x minus the initials x, and then the terminals y minus the initial y. And this will literally be 2 numbers like 2, -3, something like that. So this would mean that the change in x is 2. I'd move to the right 2. And the change in y is -3, I'd move down 3. That's what the shape would take on, or the direction it would take on. So anytime you see those little brackets, that means that means component form, and that is different from a coordinate point. So you're going to see both. You're going to see here's the coordinate points of the vector, and then you're going to see here this thing that's written in brackets like that, and that means it's component form. So that means it's an actual vector that's changing with, length and height. The magnitude is the second thing we're going to find, and that is just the length of the vector. And to do that, we use the distance formula if we're given the initial point and the terminal point. So we know the distance formula well. Square root of x minus x2 minus x1 squared plus y2 minus y1 squared. If you already have the vector form, so this would be if you have the initial point. So if you're given the points, I'm going to use the distance formula. But if I'm given the component form, either A, I already found it, or B, it's all that was given to me. I don't know the initial and the terminal. Then you find the vector form, or the magnitude, by doing the square root of a squared plus b squared. And these actually should be double lines. These should be double lines. Magnitude looks like that. So the double lines, like a double absolute value, shows magnitude. Just like every other square root, that will either be simplified. So if it's a square root that you can actually square root, you would do that. And if it's one that you can simplify, you would simplify it. So it's like square root 20, you're going to rewrite that as 2 root 5.
Are we going to be using calculators?
Not for this part. So your test is going to get split. Again, all of the law of sines and cosines is obviously calculator based. And then this stuff won't be.
we will see our quizzes.
All right, and then equivalent vectors are vectors that have the same magnitude and direction. So they have to have both the same length and the same slope. So the same magnitude, which is your length, and direction, which is like your slope. If they have the same component form, they will always be equivalent. Because if I take component form and then find my magnitude from it, it's going to be the same. But two vectors can be the same length and not be equivalent, because just because it has the same length doesn't mean it's going in the same direction. I could have a vector look like this, and I could have a vector that looks like this. And they can be the same length, right? But they're not the same direction. So those would not be equivalent. All right, example 1 says that show that U is equal to V. So these, and I'll warn you that some of this is going to happen sometimes on the notes, like it was super hard for me to draw a ray with the arrow, so you just got the ray. That technically should have an endpoint here. So it should be an endpoint. The arrow tells you which direction it's going, but these should be endpoints, and then the same thing here for the blue. Those should be endpoints. So in order for them to be the same, or in order for them to be equivalent, they have to have the same magnitude and same direction. So we're going to find both. The magnitude of U, and again, that's the double absolute value bars, is equal to, actually, let me find the component form first, because that's normally how we do it. Component form of U is equal to the change in x. So if this is 0, 0, this is my terminal point. This is my x2, y2, and this is my x1, y1. And that's important because your sign's going to change. For magnitude, it won't, but for component form, it would. So this would be 2 minus 0, comma 3 minus 0. So this is 2, 3. That's my component form. Change in x is 2, change in y is 3. God bless you. I'm going to do the same thing for V. I'm going to find the component form. Yeah.
How do you choose which one's 1 and which one's...
The arrow points to 2. Yep, this would be terminal. So this is x2, y2, and this is x1, y1. So I'd get -2 minus a -4, comma, -1 minus a -4.
Wait, what are you finding now?
The component form of V. Yeah.
To prove that they're the same, you have to find what something's component form and what else?
Actually, if the component form is the same, the magnitude will be the same, but technically by rule, it's component form and magnitude. You can't have the same component form and have a different magnitude. So this becomes plus, and this becomes plus, and I'd get 2, comma 3.
So they're the same.
So the component form is the same, and then I'm going to prove it further by finding the magnitude. But obviously, if the numbers there are the same, the magnitude's going to be the same. Now, magnitude, I have two choices. One is use the distance formula off my original coordinate points. So x2 minus x1 squared plus y2 minus y1 squared. The other is take my component form. The a is the first one, the b is the second one, and just do a squared plus b squared. So 4 plus 9 is square root 13.
What are you finding now?
The magnitude.
For each, you find magnitude?
Yeah, so we're just doing it for practice. Again, if the component form is the same, then the magnitude's going to be the same. The other way around may not happen, though.
Where do you get the A and the B?
The a and the b come from the component form. The a is the x, the change in x, and the b is the change in y. I would have gotten the same answer if I had done the distance formula. Yep.
So you don't have to find the magnitude if you already know.
If you're just looking for equivalent, yes.
Yeah.
But there's lots of, like, we are going to find the magnitude a million times between now and next week.
But to prove that, you won't just have to find it.
Correct. And then show that they would have the same magnitude, though. You do still have to show that they would have the same magnitude. It's just that you already know they will. Does that make sense?
Yeah.
Okay. All right, so then here the magnitude of V would be the square root of 2 squared plus 3 squared again, square root of 4 plus 9, square root of 13. So these are equivalent because the magnitudes are equal and the component forms are equal. So this time you actually had the choice. Like I could have used the distance formula to find that one or either of them, and I would have gotten the same answer. You just won't always have initial terminal. So if I don't have initial and terminal and I only have component form, I have to do the square root of a squared plus b squared. And sometimes you're not finding both. You might just be given the initial and terminal and just saying find magnitude, so you could just go straight to the distance formula. More often than not, we're going to end up doing square root of a squared plus b squared, but you definitely can do both if you have that information. Yeah.
And just because they have the same magnitude doesn't mean they have the same component.
Correct, right? Because I could go in a completely different direction. These could be both the same vector length, but different directions, and then they're not equivalent.
How do you say for a component form?
How do you say?
No, they're both going the same way.
The sign and the numbers on the A and the B would be the same. So 2, 3, they have to both be positive 2, positive 3.
So positive 2, positive 3 means it's going outward.
Correct. It means you would be changing x2, changing y3. So you're going like a positive slope. Yeah.
And if they were like going different directions, you already know they're not equal, right?
Correct. Yep. So in this kind of scenario where it's like show that, they're always going to be. If the question is are they equivalent, now you're getting that scenario. All right, so that question honestly doesn't happen. I think it happens like maybe once on the homework. That doesn't happen a whole lot, the show that, because we already know it's right. This is much more common. So here I'm giving you initial and, I don't know why I keep saying initial and terminal, and it's asking for both the component form and the magnitude, okay? So for A, I'll do A with you, and then you're going to do B. For A, this would be my x1 and my y1, and this would be my x2 and my y2, and I know that because that's initial and terminal.
So like the initial would be the 1.
Initial is the negative 1, 5.
Yeah.
You mean the x1, y1? Yes.
Yeah.
Yes. Where did my pink go? So for my component form, I'm going to do x2, which is 15, minus x1, which is negative 1, and then 12 minus 5. x2 minus x1, y2 minus y1. And then I'm going to add these, and I'd get 16, 7. So that's the component form of this vector, which they didn't give me a name, so I can keep it just like that. Then I need to find the magnitude. And I have two choices. One is use the distance formula from my original coordinate points. Two, if you already have the component form, skip the first part and go straight to a squared plus b squared underneath the square root. So 16 times 16 is 256, and 7 times 7 is 49. I get the square root of 305. 5 goes in here 61 times, and that's prime. I can't go any further with it. So it stays as square root 305 and component form 16.7. Yeah. Correct. Not for that kind of question.
You always want us to simplify it.
Always. Yep. All right, you do B. All right, so component form should have been 5 minus a negative 3, which becomes plus 3. 1 minus a negative 5, which becomes plus 5. So 8, 6. Then your magnitude, square root of 8, squared plus 6 squared, 64 plus 36, square root of 100, which is 10. Questions on that? Raise your hand if you got it right. Okay, good. That's like the foundation of vectors. We will use that a lot the next the next 2 weeks. All right, so a scalar multiple is a real number. So it could be a fraction, it could be a decimal, it could be a whole number that adjusts the length of your vector. So it doesn't change its direction, it literally changes its length. If you're drawing it out, and you already know that V's length looks like this, right? And then I say 2V, it goes in the same direction, so it has that same slope, but it is twice its length. If it's at a half v, it would again go in the same direction. Would it be half of the length? If it has a negative, so if the initial is positive and it has a negative, it changes the direction of your arrows. So notice this arrow is pointing up and to the right, and it switches to point down left. The negative switches direction. This 3/2 would be 1 1/2, so this would be 1 1/2 of the initial v. So if you change the sign on the scalar, it changes the arrow direction. If it's pointing up first, then it points down. If it was pointing down first, it would point up.
Because like on these, it doesn't like the bottom doesn't start at the same point. Like for.
So if you were graphing these on the same thing, they would. This is just showing you what it would look like lengthwise, but they would overlap. Like if you were drawing it on a coordinate grid, you would use that same initial point. It would just be either longer or shorter than the initial one. Yeah.
So when it starts with the initial point, or
Yeah.
the terminal be like going down?
You mean the change?
Yeah.
So on the initial, this is my initial and this is my terminal.
Yeah.
On the switched one, this is the initial and this is the terminal.
So the
They
terminal
switch.
becomes the initial one.
Yep. If you change the sign. Yep.
Can we think of this as like a transformation?
Sure. It's a stretch of the length, you could say, and the negative flips the direction. You could look at it that way.
So then let's say it's already a negative, that would make it positive.
Correct.
And then if I do a positive, scalar multiple.
Scalar. Yeah.
Scalar, that's like, it's the same, right?
It
already
just
a
extends it, makes it shorter or longer.
Okay, but let's say I have a negative already,
Yeah.
and then I multiply it or whatever by a positive one.
Yeah.
It's the same.
The direction changes. The length stays the same, but the direction changes
Because it's positive?
because it changed signs. Yeah. Yeah. Yeah.
So basically, whatever the arrow is gonna be the terminal.
Correct. The arrow points towards the terminal. And the arrow doesn't always have to be like all the way up by that endpoint. The arrow could be like all the way down here. It still means it's pointing towards you would still know where the terminal is because it's pointing towards it. The location of the arrow on your line does not matter. The other thing is what we'll do with this is you'll actually take that scalar and you'll multiply it by the component form. And you would be, so like this is if you look at it with a drawing, but then if I am given the actual points, I would multiply that number into both. I would distribute it in. So that's kind of like all these. So these are all the things that you can do with two vectors. The first is multiply it by a scalar. Well, not the first. Actually, the third one on that list. This would be if I took a vector and I multiplied a scalar by it. And for that, you would literally just distribute that number in. Okay, so since I'm on it, like the third one with the scalar, it would look something like this. It would say 2 and then maybe 1 -3. So the 2 on the front is your scalar. The 1 -3 is your component form. With these, you literally just distribute that in. And this becomes 2 -6. So if I had drawn change of 1 and then down 3, so right 1, down 3, and I had drawn that vector, and then I did 2 -6, it should continue in the same direction, but it would be twice as long if you could compare it, okay? The first one is u plus v. So I can actually add two vectors together that are in component form by adding the first one in each and then adding the second one in each. So if this was 2, if this was, let's say I'll use the same one, 1 -3 and 2 4, I would add the first 2, this would be 3, and add the second 2, and this would be 1. Yeah.
Does it always have to be a component form?
To add them, yes. I don't know if everybody heard her. Does it always have to be in component form to add them? Yes. You might have to find the component form first, but then yes, it has to be in component form to add them.
What about multiplying?
Yeah, you would still have to be the scalar's not, but the component form next to it has to be. Yeah.
The top line is the same.
That's just use like this is what I would use. So U would be U1 and U2, V would be V1 and V2, and K represents a scalar or a real number. Then I could subtract them. So if I took these same ones, it would be 1 minus 2 and then -3 minus 4. And that would be -1, -7. Order there is obviously important. If U comes first in the subtraction statement, U has to come first in each of the individual ones. And then the last thing is really just saying that a scalar that you can put that negative on the scalar, or you could take it out. So I could say that -2, -3 is the same thing as -2, 3. Those are the same things. So you can distribute in just like you can take back out. Yep.
For the orange, the second row.
Yeah.
In the first row of orange, why is there a negative outside of the -1?
It's an equals. Yeah. All right, and then actually sketching a vector. So if I gave you the component form of a vector, I'm giving you the change in x and the change in y. You use the first one as the change in x, you use the second one as the change in y, and you start at 0, 0, unless it tells you where the initial terminal point and initial and the terminal point are. If it just gives you component form, you always start at 0, 0, and then use your change in x and change of y. Plot the end, and then draw your line and arrow in the direction of where it's ending. Okay, so directions here say A, find u plus v, B, u minus v, C, 2u minus 3v, and then sketch each resultant vector. So I'm going to start with A, u plus v. So I take the first ones in each one, 2 plus 1, and then the second ones in each one, 1 plus 3. And so the sum there is 3, 4. If I want to graph this, I'm going to draw a coordinate plane. I'm going to start at 0, 0, and I'm going to go to the right 3, and I'm going to go up 4. Connect those points and point my arrow towards the terminal point. So point it towards the 3, 4. Questions on that one? All right, then I go to B, and B is u minus v. So it's 2 minus 1, and 1 minus 3. I get 1, negative 2. To graph this one, I'd start at 0, 0. I go right 1 and down 2. And I draw my arrow towards the 1, negative 2.
It's down because it's negative.
Correct, because the y is negative. Or change in y. C is 2u minus 3v. So I have to do 2 times u, which is 2, 1, minus 3 times v, which is 1, 3. First goes the scalar. So I'm going to distribute this in, and I'd get 4, 2, then distribute the 3. Now here you have two choices. 1, keep the minus between them and distribute a positive 3. 2, distribute a negative 3, but then put a plus between them. So I'm going to keep the minus, and I'm going to distribute a positive 3. Now I have to subtract them. So 4 minus 3 is 1. 2 minus 9 is negative 7.
Wait, but you keep the minus on the outside?
You could either keep the minus on the outside and distribute a positive 3, or you can distribute a negative 3, but then the in-between becomes a plus.
So what if it was just 3? What if there was no negative?
Then you would just distribute a positive 3 and then add.
Okay, thank you.
You're welcome. So I start at 0, 0. I go to the right 1 and down 1, 2, 3, 4, 5, 6, 7. And point the arrow towards the 1, negative 7.
How did you do the oh, it was 4 minus 3.
Right. Mm-hmm. Question so far? Okay, so that's one kind of, obviously the first part, adding, subtracting, all that stuff, but then that's one kind of graphing if I'm given the actual points. Then you're going to see questions in which you are not given any kind of value on your graph. So let's just say it gave me a coordinate plane, and then it gave me that u looked like that. And then it says graph 2u. So So what is that 2 doing to the u? It's doubling its length. So I don't move u at all. I just double its length. So if this is 1u, I'm going to eyeball about the same distance. That would be 2u. So I don't need it to be exact, okay? These questions on your homework will be multiple choice. It will not be like that on your test. So you're going to draw it and then pick it. So every question that says graph in the instructions, you need to make sure you have a hand-drawn graph in your homework. I put it in the instructions on Canvas, but God knows you guys don't read directions. I even highlighted it, but you'll still ignore it. Know that you have to have a hand-drawn graph for everyone that says graph, okay? If it said, and this is where it gets a little trickier. If I had 2 vectors, let's say u is still the same spot. This is u. And I have v. And I want to find u plus v. I don't have exact coordinate points, so I can't just add them together. The trick is this, okay? And it seems weird the first time, but if you practice it, I promise it's not so bad. You are going to, from the terminal point on each of these, extend a line out that is parallel to the other vector. So from u, I'm going to extend a line out parallel to v. It doesn't have to be perfect. This is kind of an eyeball situation, but I would do something like this, where that is coming out of u, but parallel to v. And then I'm going to do the same thing from the other one. I'm going to come out of v parallel to u. So it's kind of like this. And then where they meet is the terminal point of their sum. So you're basically making your own parallelogram. You're extending from each terminal point parallel to the other vector. And then where they meet is the terminal point of their sum. I'm going to do it again. So let's say vector u is here. And let's say vector v is here. I'm going to extend from u parallel to v. So it's going to look something like this. I'm going to extend from v parallel to u, something like this. And then where they cross is the terminal point of their sum.
It's just displacement, right?
Yeah, pretty much. With me so far? Okay, what if I change it now to u plus 2v? I'm going to double the length of v first, then extend out of u, which I already have, and extend out of v. And now my terminal point is here. Make sense? Okay, last thing is what if it says u minus v? What's the minus do to a vector? Huh? Flips it. It actually goes the other direction. So I start at the origin, and instead of going towards this, I go away from it. The same length, that would be negative. Now I extend from these endpoints. That would be u minus v. So you change by changing the sign. If it said negative u, I would flip the u in the other direction. If it said negative 2u, I make the u go the other direction and then double its length. You with me? Yes? Okay, because on WebAssign, there are some like both of these. There are some where you have the coordinates. I think those are easy. You just figure them out and then you plot them. And then you have some in which you only have drawings and you've got to figure that out. And both are going to happen on your test. So you got to be able to draw them without coordinates, and you got to be able to draw them with the coordinates. Questions so far? Okay. Okay, so now everything we just did in component form, we're now going to put in form called ij. I represents the change in x, or the horizontal component. Okay, I is attached to the horizontal component, or the change in x, and j is next to the change in y. Yep, sure. So if I had 2, -3 in component form, in ij format, that would be 2i minus 3j. All that changes is how we write it. These are the same thing. It's just 2 different formats. So sometimes it will ask for it in ij, and sometimes it will ask for it in component form. You just got to know how to go back and forth between the two.
So I and j isn't a variable for anything?
I represents change in x. J represents change in y. So almost the same question. It says find A, u plus v, B, v, u minus v, and C, 2u minus 3v. Then sketch the vector.
Go back to the previous slide.
Yeah, just a second. U is 3i plus j, and v is 2j. So I have 2 options. One is initially take this and put it into component form. So if it's 3i plus j, what's my component form? 3, take out the I and the j. 3, 1. That's u. And what's v? 0, 2. There's no I, so it would be 0. And then j would get the 2. That's one option. And then do everything that we just did, but with these. The second option, and to be honest, I think it's easier because at the end of these, you'd have to put the ij back in, is to treat them as though they are variables. So if I wanted to do u plus v, I'm going to add u plus v, and then combine my like terms. So 3i plus 3j. You do not put it in the brackets. Good. Yeah, no. B would be u minus v. So I do u minus v. If there were 2 terms in v, both would get the negative. There's only one. So 3i plus j minus 2j. And then combine your like terms. 3i minus j. Yeah.
Why are you putting component forming commas?
Why am I or why aren't I? So ij does not have commas, and it doesn't have brackets. That's the difference.
So you would just add, subtract all in one?
Just like that you're combining like terms. And then C is 2u minus 3v. So I'm doing 2 times 3i plus j minus 3 times 2j. And then I'm going to distribute. I'd get 6i plus 2j, distribute negative 6j, and I get 6i minus 4j. With me so far? So again, if it confuses you to keep the i's and j's, you can take it out, put it in a component form, do what we did for the first round, but then you got to pull the ij in back in at the end, because if it gives it to you in ij, your answer has to be in ij. So in my opinion, it's easier just to keep it. Now, if I wanted to graph these for 3i plus 3j, what's my change in x? 3. What's my change in y? 3. For 3i minus j, what's my change in x? 3. What's my change in y? Good. Negative 1. And for 6i minus 4j, what's my change in x? 6. 1, 2, 3, 4, 5, 6. Change in y? -4.
On the test, do we have to graph?
Yeah. Question so far? Okay, so I just want to stress that this is the WebAssign, okay? That when you are typing in the answers here, so like notice 6, it says, write the combination of the standard unit vectors I and j. You need to put it in terms of I and j. So when I go to type it in here, I'm going to hit the little box that says vectors, and then you see this ij. That's what you need to use. If you're doing it in component form without the ij, you got to use those brackets there. That's two things that it's going to pop up on the WebAssign. The other is to make sure, so when you have questions like this one, you know the coordinate points. So 5, you can just draw after you get the answers. But 4, I don't know the lengths of u and v to plot them and add those points. I have to physically, like this one says u plus 2v. I'm going to take v, I'm going to double its length, and then I'm going to draw out my little parallelogram. Those drawings have to be done on the PDF on Notability, okay? And then you can come in here and select from your multiple choice. You will not have multiple choice on your test, so I want to stress that's why I'm making you do this, okay? The other trick that I thought everybody knew, but they don't, is if you split your screen, it's not going to work because I'm on Explain Everything, but if you split your screen between WebAssign and Notability, you can actually tap and hold any of these images till they get big, and you can drag it into your Notability document. And then you have just that picture. So that's going to come in handy, especially for the ones that you have to draw.